We're going to talk about what do you need to do to write an AI that can play games. And we're going to start really simple with the most basic game there is, even more basic than tic-tac-toe, and we'll move our way to AlphaGo. Oh, and if you're here for this little guy, Gopher, yeah, he's the mascot of Golang. Yeah, that's not going to happen. We're going to talk about the board game Go. So what are we going to cover? We'll start with a very simple tree-based game. And I'll explain the basics of a tree search, which you probably already know. And I'll explain Minimax, which is an algorithm. Then we'll move to Noughts and Crosses, a bit more complex game. And then we'll talk about perfect information and game theory. Then we'll move to chess, forward-backward pruning, alpha-beta pruning. And then we'll end up at Go, our main objective. And we'll talk about Monte Carlo tree search and neural networks. Sounds complicated, but it isn't. So, I want to play a game, or as Jigsaw, not a Java 9 reference, by the way. Jigsaw, I want to play a game. It's a tree structure. You get to start, and the highest score wins. This is our tree. You can either go left, so left for the viewers, or right. Your objective is to get the highest score. What do? You go left. It has a 5, right, 3. So that's easy, right? So the first step, it's our turn. We can go either left or right. Then the opponent gets to pick. And then we get to pick. Do we go left or right? All of a sudden, this isn't trivial anymore. For a computer, it's trivial, but for us, it's like, oh, if we go that way, how do you calculate this? It turns out there's a very simple algorithm that does this for you, and it's called Minimax. What you do, you try to minimize the maximum score when it's the opponent's turn, and when it's your turn, you try to maximize the minimum score. This is perfect play. Back to the example. What do? We start at the bottom, and we evaluate those nodes. It's our turn, so we can pick the highest score. So in case of 3 and 5, we pick 5. In case of 9 and 2, we pick 9. Trivial. We assume the opponent plays perfectly as well. So when the opponent gets to pick between 5 and 9, the opponent will pick 5. He or she wants us to have a low score. And then we can work our way up, and we'll see the answer is 5. So the path you most likely need to take is go to the left. The opponent will probably also go to the left, and then you can go to the right, and you'll end up at a 5. This is optimal play for both players. If the opponent makes a mistake, you go to the left, and the opponent says, go to the right, you can go towards the 9. So that's even better. But assuming both players play perfectly, you'll always end up at 5. So this is basically how Minimax works. And it's a Java conference, so we need Java code. This is how you would implement Minimax. It's a function, and the input is a node, the starting node, and you have a Boolean if you're either maximizing or minimizing the score. If you are at the leave node, an end node, you evaluate and you get the score. So the best score, if we're maximizing, we'll start with the lowest possible integer, and otherwise we'll start with the maximum integer, and then we'll go to all the child nodes. So we move our way from the top of the tree to the bottom. And we calculate the score. And we do this by recursively calling Minimax for the child and flipping the Boolean, maximizing, not maximizing. If we're maximizing the score, our score is mat.max, score and best score. If we're minimizing, best score is mat.min, and score. And we return the score. That's basically it. That's Minimax. It's that simple. Time for some statistics. This is our game. It has a branching factor of 2. What does this mean? Well, at every point, at every node, it splits in 2. You get 2 new options. Very simple. The game depth in this case is 3, because the tree has a depth of 3. And you have perfect information. What does this mean? Well, we know the end score. we know it's a 3, a 5, a 9, a 2, a 6, an 8, a 4, and 1. So, how do you make a program that plays a game? The first thing you need is a way to generate all the valid moves. That way you can create a tree. So if you want to create a chess bot, you need a chess engine. And a chess engine is an engine that gives you all the possible moves. That's the only game-specific thing. This thing knows everything about the game. It knows the rules, it knows what you can and can't do. The next thing is you need a way to evaluate the nodes in the tree. So you need a way to score all the nodes. This is also game-specific, but it doesn't really have to do with the rules. And the final thing, which is completely unrelated to the game, is to pick a path in this tree. That's basically how you play the game. Moving on to a more difficult game, Noughts and Crosses. You all know Noughts and Crosses, right? That's a game you play in Poland as well. In Dutch, we call this game butter, cheese, and eggs. Why? I have no clue. Tic-tac-toe, okay, Noughts and Crosses. It's like noughts and crosses, makes perfect sense. But butter, cheese, and eggs, really? This is what the tic-tac-toe or Noughts and Crosses tree would look like. You start with an empty square, then you get 9 options. You can either put it in the top left square, or the top square, or the top right square, etc., etc. And below that, you have 8 moves left, and then you have 7 moves left, and 6 moves left. And at the bottom, we know what happens. You can either assign a 1 if you win, a 0 if it's a tie, or a -1 if you lose. So the evaluation function for Noughts and Crosses, because you can evaluate all the way to the end, is easy. For a computer, creating this entire tree, sure, it didn't fit on my slide, but for a computer, this is easy. It can easily generate all possible moves in Noughts and Crosses. And it can assign these values, and then you can play the game. And that's it. We can just use Minimax, calculate every possible move, and you're done. You've solved Noughts and Crosses, or tic-tac-toe. The branching factor of this game is 5. So the first time you get 9 different moves, then you get 8 different moves, then you get 7 different moves. But on average, it splits into 5. The maximum depth obviously is 9, because after 9 moves, the board is filled. And if you remove all the symmetries, there are just 138 different terminal positions. And interestingly, if X starts, X wins 91 times, the Nought wins 44 times, and there are just 3 possible positions which end up in a draw. But if you calculate all the positions in tic-tac-toe or Noughts and Crosses, and you apply Minimax to the end, and both players play perfectly, don't make a mistake, you end up in a tie. So yeah, to me that was pretty surprising, because there are only 3 tying terminal positions, but if both players play perfectly and you counter each other, you always end up in a tie. There's no way to force a win or to force a loss in tic-tac-toe. Chess. For me, chess is the perfect game. I wrote my own chess engine a long time ago just to prove I could make a chess engine, basically. And the next step, obviously, was to make a chess bot. Because, well, if you have the chess engine, you've written all the possible rules of chess, and writing a bot is basically pretty easy, as you'll see. Chess is a noble game. If you draw the tree, the complete tree for chess, you'll quickly end up, for example, when you start, I don't know, I think there are 20 different starting moves you can do. Below that, there are, for each node, another 20 moves you can do. This quickly becomes too large. Not only too large for my slide, but also too large for a computer to calculate. This table shows the problem. This table is called a perfed table. And if you would write a chess engine, you need those tables, because those tables allow you to do two things. So what is this table? When we start at depth 0, there's just one node. That's the starting board. That's how you place the pieces when you want to play a game. From that, we can do 20 different moves. So white starts, you can do 20 different moves. At depth 2, there are 400 moves, because black can also do 20 starting moves. And at that point, there's still no capture, no en passant, no castling, no promotions, no checks, and no checkmates. But after 3 moves, there are almost 9,000 different positions on the board that can happen. But 34 of them are captures, and you can even do 12 checks. And after 4 moves, there's also 8 possible checkmates in chess. This shows you how fast it grows, because even after 6 moves, there are already 120 million different positions. And a chess game doesn't end after 6 moves. Well, it can in 10,000 cases. You end up winning or losing at chess. But this tree becomes enormously large. It is so large, it's too large for a computer to calculate. It's impossible to calculate all the positions in chess and just solve chess. Would be cool if you could do it. Right now, it's impossible. So why is this table important if you want to write a chess engine? 2 things. This is very easy to implement if you have a chess engine. It's just give me all the possible moves for these moves, give me all the possible moves for those moves, give me all the possible moves. First, you'll find bugs. For example, when I did this, it had like everything was okay, except it had 809086. Fuck, there's a bug somewhere. Now I need to find it. So this is perfect for finding bugs in your, it's like an integration test for chess engines. Because you're generating all possible moves and the numbers should match up. People have calculated this for depths of 12, 13. So you can really be sure your chess engine works if you run this. Second is bragging rights. People are like, I can go to depth 6 in 5 seconds. Mine does it in 4.6. So that's another important thing, bragging rights. So the problem is there's no perfect information. We can't calculate all the way to the end and assign a value, either win or lose. That's impossible. So how do we evaluate a node? How do we give a value to a certain node? It turns out in chess, look at socks. It turns out in chess it's very easy. You just count the pieces. That's basically, if you know someone who's very good in chess, they'll probably say, oh, white is ahead 2 pawns. So that's basically how you count, you count pieces. If you've got more pieces than the opponent, you're probably winning. But that's not all, obviously. You can make a better evaluation function if you, for example, look at the positions of the chess pieces, and you look at if you've got pins, where you pin down your opponent. And you look at the liberties your chess pieces have. So the evaluation function can become very pretty and very nice, but it's easy to write an evaluation function. If you have a certain board position, and you give it to an amateur chess player, he or she can quickly say, black's winning, white's winning, or how much. So an evaluation function isn't that hard. So we can calculate up to a certain depth, maybe depth 10, and then we stop and we evaluate those nodes, and then we work our way up using Minimax. So we don't have to calculate all the way to the end. We calculate to a certain depth, we assign it a value, and then we look up. But there's obviously an horizon problem. If we calculate up to depth 10, it's looking rather good, but at depth 11, the opponent wins. Yeah, sorry, we didn't see that. So it's important to go as deep as possible, just to eliminate as much as possible. The best way to do that is to do pruning. What is pruning? Pruning, it means that you cut back branches of a tree. Oh, that's what it says. There are two kinds of pruning. You've got forward pruning, which is risky. I'll go into that depth on the next slide. And there's backwards pruning, which is safe. It's important to remember. In forward pruning, if a move is too bad for you, just don't do it. Stop evaluating. If you do a move and you lose your queen, there's no need to calculate all the positions after that, because that's probably the worst move you can do. Just stop evaluating. But also, if a move is too good, if the opponent sacrifices his or her queen, it's probably not going to happen. So we don't need to watch what happens below that, up to that depth 11, because it's probably too good for us. It won't happen. But like I said, pruning is dangerous. The most beautiful games of chess have, for example, situations where people sacrifice their queen and later turn it into a checkmate. Happens. So if you cut back the tree, you might miss this situation. Luckily, there's also alpha-beta pruning, and this is always safe. This is backwards pruning. Imagine we go all the way down, and we evaluate that node, and we do a max and a min. Max and min just means we are maximizing the score, minimizing the score, just minimax algorithm. We evaluate the next node, and it's a 5. And since we are maximizing there, between a 3 and a 5, we pick the 5. Just minimax as we did before. So we move the 5 up, and we start to evaluate another node. We go down to the same depth, and we find a 9. Because we're minimizing, and we already have the value of 5 there, and another value is a 9, we can actually stop. We don't need to evaluate any further. We don't need to go down here and find a value, because that 5 will always stay a 5. Two things can happen. This can be a very low number, a 1. But we're maximizing here, so that 9 will stay a 9, even if this is a 1. That value 9 won't change. So that value 5 won't change. This can also be higher, 15. So that 9 turns into a 15, but we're minimizing there. That will always stay a 5. No matter what happens here, that value will never change. So it's safe to prune that. So we don't need to look any further. We can stop now if this situation happens. That's alpha-beta pruning. And it also works the other way around. So here we've switched the values. The min and the max has switched. So in this case, we're maximizing. We found a 5, and there's a 3 there. Doesn't matter what happens here. If it's a 1, that becomes a 1, but that's still a 5. If it becomes 20, that's still a 3, and that's still a 5. Nothing happens. We can stop evaluating. This is the code we already saw. This is the same code as Minimax, exactly the same, but I've now renamed it to alpha-beta search. So, the first thing we need to do to implement alpha-beta search is to add alpha and beta. And in the recursive call, we also add alpha and beta. The next thing, if we are maximizing, we update alpha with the highest score. So we max alpha and the best score. And otherwise, we update beta with the minimum score. And the final thing you need to add is this. If beta is smaller than alpha, stop. You can safely stop evaluating. This speeds up your Minimax search humongously. You can cut a lot of, well, yeah, basically it's free, it's safe, and you can cut away a lot of nodes. So always try to implement it this way. It's 3 lines of code extra, and the game AI is much faster. So, how did I write my chessbot? Well, you need a way to generate all the moves, a chess engine. You need a way to evaluate the nodes. Well, we can just count the pieces, or maybe something more elaborate, but. And we need a way to pick a path in this tree, and we're going to use alpha-beta search. I did this in a weekend. was one of my weekend projects. I often do weekend projects. And I was able to write a chess engine and a chess bot, and that bot, on Monday, I've got a colleague who's pretty good at chess. He's got an ELO of 2200. It's not that good, he's not a master, but pretty good. He spent like 40 years of his life learning and improving chess. And I beat him. Just the annoying brat writing a chess engine in a weekend. And yeah, that was devastating, obviously, but fun nonetheless. So some numbers about chess. The average branching factor is 35. So on average, for each chess board you can have, most of the time there are around 35 different moves you can make. On average, a game lasts for 40 to 50 moves. Some much shorter, some longer, obviously, but on average it's between 30 and 50 moves. And writing an evaluation function for chess is relatively easy. If you take an advanced chess AI, it can look ahead for 20 plus moves. Humans can't do this. So chess has been solved. Computers are better in chess. Time to move on again. So what's so special about Go? There was a lot of buzz around the game. For those of you who don't know the game, in the Netherlands it isn't very popular, so I usually just, who knows the game of Go? Are there any Go players? Oh, a lot of people. Wow, cool. So basically it's a 19 by 19 board. There are black and white stones, and you have to surround and capture areas or limit the liberties of the stones. The first problem of Go is that the branching factor is about 250. Chess had 35, so for each step it's 35 times 35 times 35 times 35. This is 250 times 250 times 250. So it's a lot more. It grows a lot faster. And that's all because the board is humongous. It's 19 by 19, and we all know 19 by 19. A lot of possible moves. But also, the game doesn't stop after 50 moves. It goes on for 300. So if you want to calculate to the end, you don't have to calculate to a depth of 50. You have to calculate 300, which is obviously 250 times 250 times 250. That's 300 times. That's a huge number. But the most important thing is, it's almost impossible to write an evaluation function. Even the best Go players can't explain why they think someone is winning. They look at the board and they say, my intuition says black is winning, but yeah, it's my intuition. I can't program intuition. But even if you are surrounding an area and you're like one stone left to that doesn't mean anything in Go, because it can quickly change, and then it's either you get it or you don't. But so the complexity, if you would make a list of all the possible combinations you can get on a Go board, it's this number, which I can't even pronounce. But the number of positions is larger than the amount of atoms in the entire universe, which is a lot. So what can we use to play Go? Up to now, almost all the Go AIs, which aren't very good, are using Monte Carlo tree search. And if I say Monte Carlo, what do you think about? For me, it's Formula One, but yeah. But the casino. Casino is very prominent in Monte Carlo, and that's why Monte Carlo tree search is called Monte Carlo tree search, because it's based on chance, basically. How does it work? You pick a node, and you just play semi-randomly to the end. Just pick random nodes, go to the end, see if we win or not. And we do that another time, another time. We do that thousands, millions of times. And maybe we win 60% of the time, 10% of the time it's a tie, and that says something about the strength of that move. But not really. You know, it's pretty random, and yeah, but it does give an indication of the strength of that move. But it's not that good. So Go AIs aren't that good. And in 2015, just 2 years ago, the experts said it will probably take 10 to 15 years before a computer can beat a professional Go player. Forget that. Because suddenly, AlphaGo came around, and it was like this. Ah, poor baby. And AlphaGo is using neural networks. I probably don't need to explain this, but neural networks are a computer model based on our own brain. Not our own brain, but a brain in general. Time for a little demo. Maybe, if my computer allows it. We need to move this. There we are. Maximize. Who here has seen this? It's people, some people are already using this. This is the playground of TensorFlow. TensorFlow is a library where you can learn how to use neural networks. And this is their playground, where you can basically play around with neural networks in your browser. You should definitely go here and try this out. So what do we see? We can play, and we can restart, and that's about it. We have some input data. So here you can pick input. Let's pick this one. This is what our neural network is trying to solve. There are orange dots and there are blue dots, and it wants to divide those orange dots from the blue dots. And how does it do that? Well, we've got input features, for example, x. And x is a straight line. If we play, nothing happens because we don't have a network yet. Now we add a simple single neuron. And this neuron has an input weight. Maybe I can show it. Oh, yeah, I can even change the weight. And an output weight. And every time we initialize the network, it's filled with a random value, so you can see it change. If we play, we can see the network is trying to adjust and trying to solve this problem. And right now, it has found an orange area where there are orange dots, and a blue area, but yeah, it's not very good. So what does it do with this x input value? Basically, based on the weights, it can move it around from left to right. So what happens if we have two neurons? The neurons are all connected, so the x goes to the first neuron, the x goes to the second neuron, and the output is combined here. If we have two neurons, it can make two lines. And it's already getting better at separating the orange from the blue, but yeah, there's still orange in the blue area. It's not very good. So this is not the solution. Let's go back to one neuron and let's add another input. We also have a horizontal line and a vertical line in a single neuron. And as you can see, if we initialize it randomly, we can now have a diagonal line. Oh, it's not working. Sometimes it breaks. Do I have network? I hope so, yeah. Yeah, so now it has a diagonal line and it can find a diagonal area. So in this case, it found this area, which is probably better than just one horizontal line. If we have two neurons, we can have two diagonal lines, and that's already better. And to completely solve this problem, we need 3 neurons, because in that case, the neural network is smart enough to basically solve the problem and separate the blues from the oranges. But this already shows something. It's very hard to create a neural network. If we have 2 neurons, it's just not enough. If we have more than 2 neurons, well, it's enough, but if we add too much neurons, it probably takes, well, in this case, it doesn't take longer. Sometimes it takes much longer for it to, much faster, to find a solution. But if you don't have enough nodes, you can add a lot of hidden layers, for example, this amount of hidden layers. but it becomes slower and slower, and it still can't make the correct decision because it only has two inputs, two nodes every time. It even goes a bit crazy. But at the moment, we add 3 neurons somewhere. Now it has enough neurons to solve it, eventually. But a bigger neural network isn't a better neural network. It might solve it eventually or not. You know, neural networks are hard. We don't know what's happening. But yeah, check this out. It's playground.tensorflow.org, and it basically explains how neural networks work, and you can just play around with it, and it's addictive and fun. But let's go back to the presentation. Maybe. Or not. Go away. Go away. If you want to learn more about neural networks, check out TensorFlow, which is made by Google, by the way. Or check out, if you want to use Java, check out Deep Learning for J. And there are a whole lot of neural network libraries and frameworks you can use. For example, Caffe, Torch, Theno. But how does AlphaGo work? I still haven't told you. AlphaGo has neural networks. They are convolutional networks. This means that as an input, they take a Go board and they start to divide it into pieces. And each piece itself is an input node, is used as input. It's supervised learning, and it has just 13 hidden layers, which isn't that much, but they're very deep, very large. They made a couple of neural networks. This is the first one. It's a supervised learning policy network. Fancy name. But what did they do? They took 30 million amateur matches, and they gave the neural network a goal. Predict which move is going to be played next. And the network got better and better, and it was correct in 57% of the cases. Doesn't sound that good, but it actually is. Because most of the time, more than 50% of the time, it will predict the next move the amateur will play. Then they copied this network, and they gave it a new goal. Instead of predicting what an amateur would do, what's actually the best move we can do? So how did it do that? It played itself 1.2 million times. And with each time, it would update the neural network to pick the better move. Then they took Pachi. Pachi is a Go game AI, and it's not very good, but it's okay. And this network alone, without any search yet, would win 85% of the time. So that's just, given the current board, what's the best move? Do that move. So there's no searching, there's no Monte Carlo search, there's nothing, just this neural network. And this proved something. They were on the right track. But they wanted to add some more logic to this. So they wanted to have a faster network. This network, the number 2 network, took 3 milliseconds to evaluate a board. 3 milliseconds sounds fast, but in computer terms, it's not. It's very, very, very slow. So they made a new network, they gave it the same goal, but a much smaller network. And they wanted to have this, so this network is much smaller, network number 3, and it takes just 2 microseconds. Much better. So that's about 1,500 times faster. But they weren't done yet. We're so good at making neural networks, we'll make a fourth one. And this is called the value network. What does this network do? They used the same 30 billion amateur matches, and they asked it, can you predict the winner based on the current board? So this is basically the evaluation function. Initially, it had an error of 0.37, where 0.5 is obviously a random pick. And after self-play, this error came down to about 0.23. Doesn't sound very amazing, but it's much better than any evaluation function ever written for Go. So they thought, how can we test this network? How good is this? So for a given board, they would generate all the possible moves. And for all these moves, they would apply the value network, the evaluation function. And they would pick the best next move. So this isn't searching to an entire depth, it's depth 1. This was able to be the strongest known AI in Go. Still without any tree search, just this neural network. Not the other neural networks, just this one. And then they started to combine all these networks into one program, which is AlphaGo. So they used the policy network to look at the current best moves. What are the best moves I can currently make? For those moves, we use the value network to evaluate them, to give them a value. And this gives another indication how strong this move is. And then, if there's time left, they will do a Monte Carlo tree search to the end using the fast rollout policy network, the fast rollout network, to give an indication, an even better indication. So instead of random moves, we do fast, good moves, all the way to the end. And we watch at the outcome. Do we win? Do we lose? Is there a tie? This is basically AlphaGo. But yeah, how do you measure how strong your AlphaGo actually is? They set a challenge. This is Lee Sedol, and he's considered to be the best Go player of his decade. People call him the Roger Federer of Go, because apparently Roger Federer is very good at tennis, which I don't follow, but best of 5 games, and the winner gets $1 million, just so Lee Sedol really tries his best. This is the challenger, AlphaGo. It has 1,202 CPUs, 167 GPUs. Well, sounds reasonable. This is game number 1, a small video. You can see that guy over there. That's the AI slave. It's basically, yeah, the machine is doing a move, and he has to actually do the move. And this is, in the first game, move 102. And up to that point, Lee Sedol was convinced he would win, because experts said it would take 10 to 15 years before he gets beaten by an AI. But the moment AlphaGo makes this move, Lee Sedol sees something. He starts to realize, I might not win this. And you actually see his jaw drop, literally.
也应该是这样子下，也应该是这样子下，所以它的顺序也还不错的。所以就是阿法狗到目前为止，它这个不管是它脱先啊，或者它的顺序，老师你看都觉得合理，很合理。
This is a movie. He's not moving. He's flabbergasted. Wait a minute.
那理论上走到这里的话，理论上白的是要
That's when he
脱
realizes
先
he's
的
going to lose this. And that's actually what happened. He lost the first game, which was like a devastating blow to him. And he didn't even think it was possible. But yeah, AlphaGo won. Another fun moment came in game number 2. Up to that point, in game number 1, AlphaGo seemed to play very human-like. Other game AIs in Go were playing a bit like a computer, a bit weird, but AlphaGo was very human. But in game 37, something strange happened. Up to then, there are 2 commentators. They are commentating on the game, and they are analyzing the board. So right here, you can see the board. You can see AlphaGo made this move, and they are commentating on what's about to happen. But the move AlphaGo made, it's like, well, just look at their reaction.
And it changes the value of an area when you have a strong group like this, because black doesn't have any point to approach it because it's so strong.
And this is what Thore from the Google team was talking about. Is this kind of evaluation value?
That's a very surprising move.
I thought it was a mistake.
Well, I thought it was a click miss, but
a clicko. And if we were online Go, we'd call it a clicko.
Yeah, it's a very strange. Something like this would be a more normal move.
Yeah, then well, we'll just talk about what we expect, because
okay,
this doesn't make any sense.
Do you have to think about
basically
this?
what they're doing. And that was the first time AlphaGo really showed how amazing it was. The European champion Van Yu said, "It's not a human move. I've never seen a human play this move. It's so beautiful." Yeah, they're very good in, but that actually happened to chess. The game of chess changed completely when computers took over. Before that, all the humans were playing what humans are playing. It's like, I should do this, and this is normal, so I play this, and this is very logical. We always do this, so that's what we do. But the game of chess really evolved once computer chess became a thing. The game of chess currently, if you look at how the world champions are playing, it's much more creative, it's much more diverse. And this was the first time the same thing is happening in Go. And they're predicting this is going to be, the game of Go will be changing completely and will become a whole different game, maybe much more beautiful than it was before. There was another spectacular move in game 4, which was move 78. I don't have a video, but Gu Li, which is Lee Sedol's arch rival, said, "This move was made with the hand of God." Beautiful, right? But this isn't a move made by AlphaGo. This was a move by Lee Sedol. He made another surprising move, which AlphaGo completely missed. And AlphaGo made a couple of mistakes, and Lee Sedol actually won. But yeah, in the end, 4-1, he kind of got ass-whipped. So what can we conclude from this? The amazing thing is, nobody taught AlphaGo what a good or a bad move is. Nobody programmed an evaluation function for AlphaGo. AlphaGo isn't an expert system. It isn't made specifically for Go. Sure, it has Go in the name, but that's about it. AlphaGo learned by watching others and self-play. And this, to me, is really amazing, because it was using general machine learning techniques to figure out for itself how to win at Go. And already things started to happen. Like, as a response to the success of AlphaGo, South Korea announced on 17 March 2016 that it would invest $863 million in artificial intelligence research. About a month ago, there was another tourney. They took the best Chinese Go player. Chinese and Korean Go is a bit different, but his name was KG. And there was a contest, and AlphaGo again won all the matches. AlphaGo became much stronger this year. And after that, they said, we're going to stop. AlphaGo is never going to play a game of Go anymore. It's over. Because it was never the goal to win at Go. The reason they made this neural network and this entire system to optimize and self-play was for medical research. What they want to do with AlphaGo, which probably isn't going to be called AlphaGo anymore, was to predict diseases. So based on your symptoms and your past, what's the most likely disease you have? And this is the actual thing AlphaGo was created for. And I really hope they succeed.